So today I will explain about the absorption column. So firstly, this is tank B1. Tank B1, we need to fill it with water about 3/4, and then this water will be transferred to the pump 1. But in order to control the flow of water to the pump, this is the control valve. Alright? So this valve will control the flow of water to the pump 1. After it flows to the pump 1, the water will be transferred to the tank B3 up there. So from tank B3, it will travel along the pipeline to this control valve. And this control valve will be used to control the flow meter of water to be delivered to the absorption column. Okay, this is for the water. Then we move to the next part, which is the carbon dioxide tank. So this is the carbon dioxide tanks, and this is the pipeline for the carbon dioxide. So in order to control the flow of carbon dioxide, we need to use the pumps there, pumps over there to control the flow based on this flow meter. Okay. So the carbon dioxide need to be used together with compressed air. This is the pipe for the compressed air. We can open this valve in order to transfer the compressed air into the pipeline. Okay, so then this is the flow meter that will show the amount of compressed air being transferred. Up there is a mixer to mix the CO2 with the compressed air. After that, it will flow to the absorption column. So, at the absorption column, the water will flow from up to the down, and while for the air, it will flow from bottom to the up. Okay, so then I will explain about the sample. Where do we get the sample to be collected? So this is the valve that will release the sample before it is going to the absorption column. While at the back here, there is a valve for the sample to be collected after the absorption process. So that's all from me. Thank you.
Okay, right now I will explain on the desorption process using desorption column. So first, our water will flow from tank B3 to pump P2. And then from the pump, it will go into this coil at heat exchanger. So the pump will enter here, behind this. And then the water from pump will exit here at the back. And then the water will go up on this line to tank B4, reservoir B4. From reservoir B4, the water will flow to the right, and then will go down on this line. This line here. Okay, the water will flow down, and then this is our control valve to control our flow water that we can see from this flow meter. So we use this control valve to get our desired flow rate for our water, and then our water will go up to heat exchanger. The heat exchanger will heat the water to 50 degrees Celsius before entering desorption column. We can see it from here, from heater, and then the water will flow into the desorption column from at the top of the desorption column. And then the water will flow down. The water will flow down and enter back at this heat exchanger before going back into our reservoir B2. So for this option, we will supply air here to dissolve CO2 from our supplied water. So the air will enter from below of the desorption column. We will control the air flow meter by this valve, and we can see the air flow meter here at this flow meter. So we can control it for our designated for our desired flow for air, and then we will keep constant both of the flow air and flow water for 15 minutes until 10 to 15 minutes until the reaction stabilize, and then we get the result. For the result, after 10 to 15 minutes of the flow of this desorption column, we will take the before water dissolve in the desorption column from here, from this valve, and then we will take the sample for water after desorption from this valve. We will take the water before the desorption from this valve, and then after desorption from that valve. Okay, that's all for desorption column. Thanks for watching. See ya.
After we do the absorption process, so this is the water sample that we get from the absorption column. Now we're going to do titration process. So before that, we're going to measure around 100 ml of the sample. Make sure your eye is perpendicular to the scale. Right, and then, okay, it's enough. 100 ml. Then transfer it into the conical flask, which will make it easier to do the titration process. Okay, now we're gonna put some few drops of phenolphthalein, around 5 to 10 drops. So I just drop 5, I think. Alright, 1, 2, 3, 4, and 5. Okay, now we're gonna do the titration process. Make sure you open it very slowly so the water drips, and stir it gently. Right. While the water drips, stir it gently until the solution turns into pink. So the phenolphthalein is the indicator that we use to detect the carbon dioxide in the water. So we need to wait until the titration process make the sample turns into pink, and then we can measure the carbon dioxide content in the water sample based on the sodium dioxide that we used while we titrating the sample. Alright, I think that's all from me. Thank you. Alright, for the introduction part, so my name is Tengku Rifki. Will present about the introduction part. So now we talk about absorption column. So absorption column basically is a unit operation of mass transfer which separates some components of gases by contact with an adequate solvent. Usually, absorption process happens to recover solvent vapor, gas treatment in refineries, and also function to the decontamination of industrial gases. So I also put a picture of absorption column. Now we're gonna proceed with experiment absorption, which is the absorption of carbon dioxide into water and its desorption with the same water flow rate. That's all.
Okay, hi, my name is Nur Atika Aina binti Hamzah. My matrix number is 191867. Okay, for this report, I'm going to present about the background and the theory for absorption and desorption. Okay, so gas absorption or desorption is a process in which a gaseous mixture can be brought into a contact with a liquid, and during this contact, a component is transferred between gas stream and the liquid stream. The principles for both systems are the same. The gas is either dissolved in the liquid, which is or extract a volatile compound from the liquid, which is desorption. In a bag cover with a gas or packing M type, it has an upper limit to the rate of gas flow, known as floating velocity, of which the tower can operate above the velocity mentioned. So for the principle, at low gas velocities, the liquid flows downward through the packing uninfluenced by the upward gas flow. As the gas flow increases at low gas velocities, the pressure drop starts to rise at a high rate. The liquid accumulation increases as the gas flow rate is increased. At the floating point, the liquid will no longer have the ability to flow down through the packed column, and later is blown out with or by gas. For the packed tower, the packed column can be operated in concurrent as well as countercurrently. Countercurrent flow is preferable since the contact time between the liquid and gas is greater. The liquid flows in downward direction over the surface of the packing driven by the gravity force. The gas flow through the space of the packing in upward direction driven by pressure.
Okay, hello and a very good day. I'm Nurul Izzati binti Yusof with matrix number 191958. So today I'm going to explain on the results for experiment 7 and 8, in which for experiment 7 is the absorption of carbon dioxide into water with water flow rate of 110 liter per hour. So based on table 1, we can calculate the rate of absorption from carbon dioxide into water with respect to time. So basically the liquid from vessel B1 is the sample before, and for the liquid from valve B9 is the sample after. After doing some calculation, we can find the rate of absorption. So basically the concentration of the figure 1 shows the graph of concentration of NaOH used with respect to time, in which we can see that the concentration of NaOH, sodium hydroxide, before is lesser than the concentration of sodium hydroxide used after for the absorption. And this is the rate of absorption with respect to time, in which the trend increases and after 20 minutes the rate of absorption decreases and become constant. For experiment 8, which is the desorption of carbon dioxide from water with a water flow rate of 110 liter per hour as well. Okay, so basically liquid from vessel B2 is the sample before, and the liquid from valve P16 is the sample after. And after doing some calculation, we can find the rate of desorption of carbon dioxide from water. So now we are going to proceed with figure 3, which shows the graph of concentration of sodium hydroxide used with respect to time. Okay, so basically we can see that the concentration of sodium hydroxide used before is much greater compared to the sample after. Okay, now we can see that the figure 4, which is graph of rate of desorption of carbon dioxide with respect to time, in which the rate of desorption increases and then decreases slowly with time. Okay, that's all from me. Thank you.
Hi, my name is Wan Nazihaliana binti Wan Joshua and my matric number is 192032. I am from group 2 and I will continue with the presentations. So I am doing my part, which is the discussion part. Based on the result that being explained from my friends previously, we are doing experiment 7 and experiment 8, which is the absorption and desorption of carbon dioxide. So from experiment 7, the amount of carbon dioxide being absorbed into water increasing with time based on the amount of NaOH used in the titration. The rate of absorption is increasing as the time increases until it reaches 20 minutes, and it starts to decreasing at the time of 30 minutes, and after that it starts to being constant. For the experiment 8, which is the desorption of carbon dioxide, the amount of carbon dioxide being removed from water is decreasing with time based on the amount of sodium hydroxide used. Rate of desorption is increasing as the time increases until it reaches 10 minutes. After that, it starts to decreasing until it reaches 20 minutes. After 20 minutes, it starts to be constant for 10 minutes and then it decreasing again. So, the mass transfer of carbon dioxide from the gas to the liquid is a fast reaction, and it is well explained in the Fick's first law. The driving force for the transfer from the gas phase is by using the concentration gradients, and it can be estimated by using the partial pressure of carbon dioxide, while for the transfer in the liquid phase, it is estimated by using the concentration difference in the films of the liquid. For these experiments, we use titration process in order to estimate the amount of carbon dioxide content in the sample. By using the titration process, we use sodium hydroxide and phenolphthalein as our indicator. So the absorption of carbon dioxide occurs when the surrounding is dry, while the desorption of carbon dioxide occurs when the surrounding is wet. For example, I explained about the experiment that we did in the lab. For the absorption process, we take the carbon dioxide from the dry part and it is removed or it is absorbed into the water. So it means it's from dry to a liquid. While for the desorption process, the carbon dioxide is contained in the water, which is a wet surrounding, and it is being removed to the gas phase. Then, I will explain about the flow rates of water that impact the amount of carbon dioxide absorbed. The flow rate of water will impact the amount of carbon dioxide absorbed into the water because as the flow rates of water increases, the amount of carbon dioxide being absorbed is also increases. By using this process, we need large amount of water for the absorption of carbon dioxide, and this is explained by using the atomic stick simulation that involve the reaction-free energy. For this process, the reaction-free energy is refers to the carbonated ion. The pH of the water or pH of the solvents also affect the rate of carbon dioxide being absorbed. As the solvent become more acidic or more alkaline, the rates of absorption will be decreased. The desorption is a process of removing the carbon dioxide from water. By using these experiments, it is usually done as stripping. Okay, during the experiments, there is some problem that we face. First, it is not easy to control the flow rates of water, carbon dioxide, and compressed air since it is used manual valve. So each of us need to monitor the valve. The amount of carbon dioxide present in water sample are not being measured correctly since it is used the titration process. For the recommendation that we can use to improve the experiment is we need to make sure that the system is stabilized between 10 to 15 minutes before the experiment starts in order to get the actual result. As we all know that any system need to be stable when it is shut down or open for the experiment. So 10 to 15 minutes is a best time for the system to stable before start any experiments. Then we need to make sure that all flow meter is being monitored in order to avoid the changes of the flow rates. In this experiment, there is 3 types of flow rates that we are monitored, which is first is compressed air, second is the carbon dioxide, and the third one is the flow rates of water. So the flow meter need to be monitored by each of us to make sure that the value of the flow rates, water, carbon dioxide, and compressed air is at the constant levels throughout the experiments. So I think this is all about the discussion, and thank you.
Hello, my name is Abu Huraira bin Abdul Wahab Sa'loni. My metric number is 191900. From this experiment, we can conclude that the rate of transfer of gas to liquid and liquid to gas is heavily dependent on the concentration gradient of the substance. Since rate of transfer of gas depends on concentration gradient,
pH value also affect the rate since it shows the presence of other substance in the solution, which can change the concentration of the solution. It also affected by time, as we can see from the result. The rate of transfer of gas in experiment 7 increased for the first 20 minutes and then will gradually decrease, while in experiment 8, the rate of transfer of gas increased for the first 10 minutes and then start to gradually decrease for the rest of the experiment. I think that's all for conclusion. Thank you.